Let's review how we got to this point. Okay? We wanted to solve a linear system AX equals B. But if A is overdetermined, if A has more rows than columns in it, then usually the best we can do is find the approximate solution, AX equals approximately equal to B. And what we're interested in is the best solution for this. Okay? And what we reasoned was that instead of solving the linearly squares problem, what we can instead do is solve the normal equations. And how do we get from there? Well, I always remember this by saying, okay, you get to the normal equations by just multiplying both sides by a Hermitian transpose. So now we have the normal equations. Now, you can't just blindly do that. It's the theory that we developed that tells us that this then is the best solution. But let's move on. And then you say, well, okay, now I have the normal equations, but I need to solve the normal equations. And notice that this now becomes an equality. Well, one way you could do that is to say, okay, we'll compute this vector right here, y. That's a matrix vector multiply. And we compute this matrix right here, b. And then what we're left with is having to solve b times x hat is equal to y. Now notice that b is now a square matrix, because a Hermitian transpose times a gives you a square matrix. If a is m by n, then this matrix is n by n. And we already commented on the fact that if A has linearly independent columns, then B is a non-singular matrix, and therefore we know that this has a unique solution. Okay, now the question now becomes, how do we solve this? Well, one way is to say, well, mathematically this is the same as computing x hat is equal to B inverse times y. Well, mathematically that's all very nice, but we don't know yet in this course how to compute the inverse. You may have been taught how to compute the inverse of a matrix in some other course. But when I teach an undergraduate linear algebra course, I stress you should never, ever, ever, ever compute the inverse of a matrix, except in very special circumstances. So, never, ever, ever, ever compute this. And one of the reasons why you don't ever, ever want to compute this is because there are alternatives for solving this that are intermediate steps towards computing B inverse, and therefore it's actually easier to just use those. Now, what are those alternatives? Well, you may have been taught in an undergraduate course that you can take your B and compute its LU factorization, where L is a unit lower triangular matrix and U is an upper triangular matrix. And then you can use that LU factorization to solve for x hat. Rather than going into the details of that, let's actually go to how one usually does it when it comes to solving the normal equations. And that is to observe that B is not only a square matrix, but it actually is also a Hermitian matrix. Okay? If you look at B Hermitian transpose, that is equal to a Hermitian transpose times a Hermitian transpose. And you may remember that what you do is you flip the order of these two, and then you take the Hermitian transpose of each, but that of course is just A, and you notice that it is actually equal to B. So, it's Hermitian. It is symmetric, except in the complex sense. Alright, so that's nice. So how can we take advantage of that? Well, it's not only Hermitian and square, but it actually turns out to also be symmetric positive definite if A has linearly independent columns. And what that exactly means we'll get into in a future week. If a matrix is symmetric positive definite, or Hermitian positive definite in this case, then you can actually factor it into a lower triangular matrix times its Hermitian transpose. And how does that help us? Well, we're going to see how to compute that in a future week. But let's just say that we know how to do this. What do we do with the result? Well, we want to solve b times x hat is equal to y. We can then substitute in for b L times L Hermitian transpose. And then we can place some convenient parentheses. If we then say, well, we don't know what this vector is, but we can call it z, then what you notice is that L times z is equal to y. But you know what L is if you've computed the Cholesky factorization, and you know what y is, and therefore you can now solve with this lower triangular matrix. That's solving a lower triangular system. That's relatively easy. And then once you have your vector z, you remember that L Hermitian transpose times z is equal to y. But notice that a lower triangular matrix, when you compute its Hermitian transpose, gives you an upper triangular matrix, and solving with an upper triangular matrix is relatively easy as well. Now, you wouldn't want to explicitly transpose L, because that would require a lot of data movement, but you want to compute as if it is an upper triangular matrix. And what that means is, whoops, we don't want to do that. We want to put z here and we want to put x hat here because it came from here. And notice that once one actually solves that linear system, then one is left with the solution that was desired. Okay? So, other than that, we haven't talked yet about how to compute the Cholesky factorization and the theory related to that. We now have an actual computational method for solving the linear least squares problem.